Alright, so it's 11:02. What I thought would be quite nice is to actually make a quick start because we'll not be able to finish on time if we don't make a quick start. And the other session they can just catch up with the recorded tutorials if that goes okay. I know that a few previous tutorials they were recorded. They had a bit of an issue with audio quality, but that's because I'm not very familiar with Google Meet and how to record the screen actually. Regardless, I mean, people who are here, you know how to use the syllabus already. That was what I've shown you how to do. And that's what we're going to do here today with rate of reactions. So last week, I talked about 6.2, which was redox. And I know that most of you, I did clarify last week, most of you are doing the 2022 O-level exam. So this is the syllabus for your 2022 curriculum. It is stated that for exam in 2022, there is a bit of a small change. There isn't so much big changes for the 2023 rate of reactions, but there is a bit of a small change in wording and stuff. So ignoring the redox there, we're just going to go through rate of reactions. Syllabus document doesn't show you a lot of things, but there's actually a lot of details that you can find out from there. Can I just double check? Can people hear me?
Yes.
Alright, okay, just in case. Alright, I was just worried that I turned my microphone off. When you are going through tutorials, you really should really write down some stuff and rather than just watching, because you don't want people to tell you that you are a visual learner, no one learns by just one method. Ideally speaking, in sciences, you have to write, watch, draw, do, a combination of all of those things together, yeah? And of course, thinking as well. Describe. So describe means you need to go into a little bit of greater details. What is the effect of this factor? Concentration, factor number 1. Pressure involved gases. Particle sizes is basically surface area. So whether you talk about surface area, particle size, that means the same thing. And last but not least, there's temperature as well on the rates of reaction. We need to think about in terms of collisions between reacting particles. So I'm just going to quickly talk about something called the collision theory. So you know that for two things to react, they have to collide. Okay, for reaction to happen, they have to collide. Particles must collide. That is the number one thing. If they don't come into contact with each other, they don't collide, there is no reaction. So for reaction, particle must collide. But there are certain conditions. They must collide in the correct orientation. If you think about enzyme lock and key mechanism, you cannot collide in wrong orientations, otherwise they don't fit into the lock and key kind of mechanism. So for other chemical reactions to happen, they have to collide in the correct orientations, and then they have to collide with enough energy. So this is N with enough energy. Why must we have enough energy? Because we must overcome this thing called activation energy, activation barrier. Every single reaction has an activation energy to be overcome, so that when you want to go to the other side of the reaction, I'm just going to draw reaction profile diagram. Reaction profile diagram show you the progress of reactions, or you have reaction coordinate on the x-axis, basically going from the reactants to the products, what happened. We can show for an exothermic as well as an endothermic reaction. So this relates to enthalpy changes topic, which we did cover before, if I'm not mistaken. So if I show for an exothermic reaction, let me show for endothermic first. Endothermic reaction. In an endothermic reaction, my delta H is positive. That is because my reactants absorb energy from the reactants to the products. So the products will have higher energy than the reactants because I absorb energy. I mentioned previously that your direction really matters. You cannot use a double-headed arrow from the reactant to the products. It's going up, that's why it's positive. The reactants absorb energy to form the products. The products have higher energy than the reactants. This is an example of an endothermic reaction. So that thing there, from the reactants to the product's energy level, that is your delta H. It represents enthalpy changes. And this pink colored thing that I'm drawing it, from the reactant to the top of the peak, that is called activation energy. That was the thing I was mentioning. Particle must collide in the correct orientation, and they must collide with enough energy to overcome this activation energy. This is the activation energy for an endothermic reaction. Before you want to go to the products, you must overcome this slope here. And if you don't have enough energy to overcome that, then you are not going to go to the other side. You're not going to react. You just go back to being reactants. On the other hand, when you have exothermic reactions, these are all terminologies which you will have come across. Delta H is lesser than 0, so you will have reactants that will lose energy. So the reactants lose the energy because then the products will have lesser energy than the reactants. So your delta H is coming down. Your delta H is coming down. That is why it's lesser than 0. It's coming down. It's decreasing because this is a y-axis. The energy is increasing that way. The energy is decreasing that way. The products have lesser energy than the reactants because the reactant lose the energy to form the products. This is what happened to the reaction. Where does this energy go to? It releases the energy to the surrounding, which happen to be the solution or the air around you, and that surroundings will get hotter. You will see an increase in temperature because that is what you see on the outside. So I'm just drawing just what happened there to complete the energy profile diagram. From the reactant to the product, I also have a slope to overcome, and it has to go upwards because from the reactant to the top of the peak, that is what you call the activation energy of the reaction. So that looks different because this is for endothermic reaction. The delta H is greater than 0. Exothermic reactions, the delta H is lesser than 0. A couple of terminology that you have to know in this topic. One of them is called activation energy. So how do you define activation energy? This could be a 1 to 2 mark question. So activation energy is the minimum energy. You think about you needing to overcome that slope there. Minimum energy that your reacting particles, your reacting molecules must possess in order to react. So if a reaction has a high activation energy, if this barrier is very, very high, your reaction is going to be slow. If your activation energy is small, it's very easy to get to the other side. Your reaction is going to be fast. So the idea is that high activation energy, not easy to overcome, equal to slow reactions, and vice versa. You will have a fast reaction when you have low activation energy. In terms of the factors, so when you are explaining, the factors affecting rate of reaction, so people think that this topic is actually quite easy, but there are some stuff that you cannot get wrong. So this is to do with temperature, and then this is to do with surface area, for instance. And then one other thing was to do with pressure. So pressure will affect gases. So some reactions involve gases, whereas most of your reactions involve solutions. So we need to talk about concentrations, and that involve solution chemistry there. So in terms of these 4 factors, we need to think about how to explain each and every one of them because you can get each and every one of them. As temperature increases, rate increases. The question is, how do you explain it? Okay. Temperature is a measure of kinetic energy. If you do physics, you know that temperature is directly proportional to kinetic energy. This is also true from your states of matter heating curve. When you increase temperature, particles gain more kinetic energy. So we say that as temperature increases, your reacting particles gain more kinetic energy. As they gain more kinetic energy, they will move faster. Because kinetic energy is to do with movement, so they move faster. They move at a higher velocity, at a higher speed. So what happened then is the particles will collide more. So collide more there refer to more frequently. So they come into contact with each other more often. As they collide more frequently, therefore, rate increases. So these are the key points in terms of kinetic particle theory. The very first topic is called kinetic particle theory. What happened to the particles explained in terms of kinetic particle theory. What happened to the particles as temperature increases, that explains the rate increasing. There are always some keywords to look up for. You do not want to lose some easy marks on rate of reaction. Easier said than done, obviously. Surface area is to do with contact, so contact point. So you will have powdered form, powdered versus lumpy solid. So lumpy is like, if I have a cube that are like that, so my cube is not the best in the world, versus if I have the powdered form, So this thing here, the powder form, will have a larger surface area. So if you have a larger surface area, think about when you dissolve a sugar cube, if you crush it into sugar powder, or if you have a big block of sodium chloride versus a very finely powdered sodium chloride, this one is going to dissolve a lot faster than the other one. So the larger surface area will have a greater contact point, and this contact point is where the particles can collide more frequently. So your reacting particles collide more frequently. So again, we come back to that idea of more frequent collisions, and therefore overall rate can increase there. In terms of gases have pressure. So pressure and concentrations are quite related in the sense that, at higher pressure, when you have higher pressure, you are squeezing the particle closer together. So the particles are closer. When they are closer together, they will collide more frequently. And when they collide more frequently, again, the rate would increase there. I'm sorry that my partition is not the best in the world here, but I'm running out of space here. So what happened with concentration? Concentration is in mole per dm cube. So that means how many moles in 1 dm cube. Based on the unit, it means how many moles in 1 dm cube. So if you have higher concentrations, what does higher concentration means? Higher concentration means there are more mole per unit volume. If there are more mole per unit volume, that means there are more molecules per unit volume, because you can relate the number of mole to the number of particles. That was from your mole concept. So if you have more particles per unit volume, they will collide more frequently. And if they collide more frequently, your rate of reaction is going to increase definitely. Okay, just in general, those are the explanations. When you go back to the syllabus, you will see that there's also defined the term catalyst. So you should be able to prepare a 2 marks definition for this. There are one thing about speed up the rate of reactions, makes the reaction go faster. But one thing about catalyst is that its surface remain chemically unchanged. Its surface is chemically unchanged at the end of reaction. If you put in 1 gram of catalyst at the beginning, so suggest what is the mass of the catalyst you will get at the end of reaction. Because it is a catalyst, its surface will remain chemically unchanged. Its surface is not used up at the end of reaction. You will still get the exact same mass of what you put in at the start of the reaction. So I assume that all the students who do chemistry will have done biology as well. And the idea of enzyme is that it is a biological catalyst. Anything to do with biology, they are sensitive to temperature, they're sensitive to pH, and most importantly, they work by this lock and key mechanism, where this idea of colliding in the correct orientation is very important. You're not going to form the enzyme substrate complex. You cannot get metabolism if you don't fit into the enzyme active site correctly. This very next thing, part C, is about this pathway with a lower activation energy, increase in rate of reaction. Why is the rate of reaction getting faster? Rate increases because lower activation energy, as I mentioned from the reaction profile diagram. How is the activation energy lower? Because there are different pathway. Why is there a different pathway? Because you use a catalyst. So what does a catalyst do? A catalyst simply, they don't just destroy the original activation energy. What you still have is, you still have the reactant going to products. I'm just going to draw one here for these exothermic reactions. So this reactant is going to this product. We know that that is exothermic reaction. And then rate of reaction, you cannot tell rate from this enthalpy change because this bit is not activation energy. Rate of reaction depends on activation energy. If that is my activation energy, uncatalyzed. So what will happen when I use a catalyst? I'm just going to magnify this a little bit. When I use a catalyst, I will have a lower activation energy, but I still go from reactant to products. So my reactants and energy level, my reactants and products energy level is still the same. So whether I use a catalyst or not, the enthalpy change remains the same. You will see, let's say this is catalyzed, this is still lesser than 0. And then the blue one is uncatalyzed, that is still lesser than 0. So using a catalyst, this is one of those multiple choice questions. Using catalyst will not will not change delta H, as you could see from the diagram. What change, however, would be the activation energy. You will see that there is a different pathway from the reactants to the top of the peak. This is now the activation energy of the catalyzed reaction. The activation energy is still positive, it's still going upwards, but you have a slightly less slopy hill to overcome. So we can say that the activation energy catalyzed is going to be lower than the activation energy uncatalyzed. So using a catalyst, what does a catalyst do? A catalyst offers an alternative reaction pathway. There is always another option. This is called alternative. You don't like this word, you can use optional. And then this is reaction pathway. You don't like pathway, you can use reaction route. It does not matter what words you use, as long as you know about the technical details and tell the story correctly, you will still be correct. And what is wrong, actually what is not wrong, but what is different about this different pathway, alternative reaction pathway, different pathway, the difference is lower activation energy. So this alternative reaction pathway has a new and lower activation energy. Your old activation energy, which was uncatalyzed, is still around. It's just that this new lower activation energy is different from the previous activation energy uncatalyzed because you have a different pathway. Overall, since the activation energy is lower, your reaction is going to be faster. That was just basically describe how catalysis work. Now the next bit is basically a little bit of transition metal chemistry. If you are halfway through your second year of O-level, and if you are sitting for your O-level this year, you probably would have done catalysts in transition metals, and enzymes are biological catalysts. I already talked about that. Industrial processes in 8.3, I can tell you briefly about that. So first one is what you call Haber process. So in Haber process, you are making ammonia, and this is an equilibrium from N2 and H2, and this is gas, and 2NH3 gas. So there are some other conditions in there. As you will see in reversible reactions, there are some reactions there. But what is important is you use an iron catalyst. You use iron as a solid. You use the transition metal, solid transition metal. It has metallic bonding, obviously, because it exists as a metal. Now you also have a contact process. So contact process is used to make the sulfuric acid, but the only reversible step is the one that formed the SO3 from the SO2 reacting with O2. Balancing your equation, you're going to get that because you do not ever write any equations which are not balanced. This thing there is called vanadium 5 oxide. So last week, I think I talked about oxidation number, but they did say for the 2022 Cambridge International O-Level, oxidation number is not required. But then this V2O5 is vanadium 5 oxide, so it is an oxide of metal. It is an oxide of transition metal. Metal and non-metal, they can ask you on bonding. So this is definitely giant ionic structure. It will have a high melting and boiling point. That is why it's going to be a solid. You use it as a solid V2O5 catalyst there. Now there are some other catalysts. One more is to do with your organic chemistry. I believe that you might not have done this. If you haven't finished your syllabus, you would not have done this. This is as part of alkene chemistry, where you will have things like carbon-carbon double bond, and then you can add hydrogen. You add hydrogen across, so you are no longer having carbon-carbon double bond. You will learn this eventually. So this is your addition of hydrogen onto carbon-carbon double bond. So did you learn this? Yes, you do, because define oxidation and reduction in terms of oxygen and hydrogen gaining or losing hydrogen there. This definition is pretty useless when we talk about metals and non-metals. This definition is more useful when you talk about organic chemistry. I think I talked about it last week. So what is meant by reduction there? Reduction is when the carbon, this carbon, and this carbon gain hydrogen. Both the carbon gain hydrogen. Both the carbon gain hydrogen. Gain of hydrogen is what you call reduction. So this thing has been reduced. This thing has been oxidized. So the H2 has been oxidized. The alkene has been reduced because both carbon gain hydrogen. So this overall reaction is known as redox reaction there. Okay. But of course, you can also call this as addition reaction. So if you call this as addition reaction, you could also call it as hydrogenation reaction. That's very typical in O-level chemistry. And I haven't mentioned about the catalyst yet. This uses nickel, or sometimes they can say platinum catalyst. So platinum is more expensive, but nickel and platinum, they are in the transition metal series, the middle block of the periodic table. Transition metals make very good catalysts. Now, I'm not going to talk about E and F in the context of explaining, but we're going to talk about E and F in the context of the questions actually. So that's pretty much it on rate of reactions. What I thought would be quite nice is to actually go through some questions. I uploaded these question papers a bit late. Sorry about that. Totally forgot about that until yesterday. They are in the Google Classroom materials, so you can download the paper 1, paper 2. You're more than welcome to try as many or as little as you want, obviously. As with everything in life, try as much or as little as you want is up to you. But the more you do, the more you improve, provided you ask for feedback. Okay? Don't just do without knowing whether it's correct or not. Don't just mark your work without knowing whether you would actually have done it correctly or not. Okay? So these are MCQ paper 1. There is also a paper 2 structured questions with the year. Do not try and go straight to marking scheme. The idea of past year papers is never to look at the marking scheme, because there is no marking scheme in your real exam, in your real test. You will have to practice doing questions first without referring to anything. Okay? And of course, if you don't know anything, just go through the syllabus again. I have also uploaded this thing here. I thought this is probably the first question I want to go through together with you guys first before I open the floor for you to ask questions. So let me just quickly go through this, alright? So this is a hydrochloric acid, and this is added to powdered zinc. So we know that HCl plus zinc will give us a salt. This is metal, this is acid. So we'll get a metal salt. The salt that we get depends on the acid that we use. If we use HCl, we will get a chloride, not chloric, chloride salt. If we use a sulfuric acid, we'll get a sulfate salt. If we use a nitric acid, we'll get a nitrate salt. Now the thing is, this is metal. The metal salt will be zinc chloride. Zinc, when they form ions, is Zn2+. Chloride ion is Cl-. These are from the list of ions as stated in your syllabus, and they are also in the 2 pages of practical tests if you have ever done analysis of cations and anions. And they are also in paper 4 as part of qualitative analysis, and you will not be given the table of results. Therefore, you must know all the tests for cations, anions, and tests for gases. 2 and 1 refer to the valency. These are the combining powers based on the charges. The charges is 2+, so the valency is 2. The charges is -1, the valency is 1. This is called lowest common multiple. How to get the formula of compound? You do the cross multiply or the crisscrossing of the valency. This is how many, so you need 1 of that zinc 2+, because this left hand side is all zinc 2+, 1 of that. Need to cancel out the charges from 2 chloride. The salt that you get is ZnCl2. You also get hydrogen gas because this is a metal plus acid. Whatever equation you write has to be balanced in O-level chemistry and beyond. So this hydrogen gas evolved can be tested. As you know, hydrogen gas can be tested. I'm going to ask one of you to tell me the test for hydrogen gas. It is in your syllabus. Okay? Alice, are you there, Alice? Hello, Alice, are you there? Hello, Shami, are you there? Hello, Shami, are you there? Okay. Hello, Shakila, are you there?
Yes.
Hi, Shakila. What is the test for hydrogen gas? What is the test for hydrogen gas?
The lighted splint.
So you use lighter splint. What happened to it?
If you put it in hydrogen gas, it should rekindle.
It doesn't rekindle because I can tell you, hydrogen reacts with oxygen, you get water. Water does not support fire. You use water to put out fire. So how can you put
the pop sun?
Okay, so you need to think carefully about what you're producing. So very clearly, you are confused between the tests because you don't know the underlying chemistry. Hydrogen burns in oxygen to give you water. Water is what firemen use to put out fire. So the fire doesn't become brighter and heavier and become it doesn't relight because water put out fire. So it burns with a pop sound. That is the characteristic test of hydrogen gas. Anyway, so looking at this thing here, you have metal A, B, and C, and we measure the volume of hydrogen against time. So the volume of hydrogen produced against time will tell us the rate of reaction, because rate is to do with change in amount, how much changes over the time taken. So change in amount over change in time. They want you to identify metal A, B, and C from zinc, magnesium, and aluminium. Now, graphical questions, there are two ways to analyze it. Okay? So first of all, the first thing you should notice is, do you see that this one produce a greater volume of hydrogen? So this is volume of hydrogen gas there. But then we also have A and C there producing lesser hydrogen gas there. Why are they different? If you read the question, the whole question from the very beginning, you will see using the same mole of powdered magnesium and aluminium. Using the same mole of powdered magnesium and aluminium, you have three metals. You have zinc, Zn, you have magnesium, and you have aluminium. Okay, when we form the salt, we are going to get zinc plus just now 2HCl, give you ZnCl2 plus H2, like that. When you form MgCl2, it's going to have the exact same equation, MgCl2 plus H2, like that. And then when you have aluminium, it's going to follow a different ratio, because aluminium, when they form cations, Al3 plus, Cl minus, 3 and 1 is going to be your valency. And then when you do the crisscross, you're going to get 1 Al3 plus, balancing out the charges of 3 Cl minus. You're going to get AlCl3 and H2. Because we use the same mole of zinc, magnesium, and aluminium, because the question says same number of moles, so I must keep this 1, 1, and 1. You don't like to balance equation with fraction, I know. In O-level, a lot of teachers, they don't like to teach the students with fractions. But you cannot choose because same number of mole, 1, 1, and 1, according to the question. So I must have 1 aluminium. If I have 1 aluminium, then I must have 1 there to give me 1 aluminium. Then there is 1 times 3, which is 3 chlorine. 3 chlorine there would mean 3 HCl. 3 hydrogen there means 3 hydrogen. You cannot put a 3 in front there because 3 times 2 is 6. You only want 3. You cannot change the identity at the bottom because hydrogen is a diatomic gas. What you can do is 3 over 2, because 3 over 2 times 2 is 1 mole. 3 mole. What am I talking about? Okay, so you get 3 hydrogen atoms there. So not 3 mole, 3 hydrogen atoms there to balance the 3 hydrogen atom. The very reason I use fraction here is because same number of mole of each of these, according to the question, same number of mole for magnesium and aluminium, the powdered zinc. Based on these 3 equations, you can see which one will give you more hydrogen. If you use same number of mole, the aluminium will give you greater number of hydrogens. I hope you can see that. That is why metal B must be aluminium, because you get more hydrogens from the same mole of the metal. Whereas A and C, same number of mole of hydrogen, because you get 1 mole and 1 mole of hydrogen from the same metal, same number of mole there will give you same number of hydrogens. Okay, hopefully that is the first thing you notice. The second thing you must notice, so I should be able to identify metal B as aluminium. Metal B is aluminium. And how can you give the reasons? Well, I can give this thing here. I can give my 2 equations as my reasons. So that thing there. So greater mole of H2 gas. So greater mole means greater volume. I can talk about greater mole, or I can talk about greater volume. Both of them will give me the marks there. Anyway, going back to the idea here. Now, you need to think about something called rate of reaction, reactivity. You have learned something called reactivity series. So people will talk about reactivity series like the polycarmazole. Potassium, that's the po, and then the so is the sodium. We do not write PO because PO is actually polonium, but the way you remember it is potassium is the K, is the correct symbol from the periodic table. Potassium, sodium is Na, not SO. Please know the correct symbol. Polycarmazole, so that is Ca, and then this is your Mg and Al. So there's the Paul, so, Ka, M and A is your Ma, and then your Zil, that is your zinc, and then ZIL, so the next one is iron, and then the next one is lead, and after that what you get is hydrogen. And copper, sorry, not copper, carbon. Carbon comes somewhere there, and carbon is quite important because sometimes you use carbon as a reducing agent. So you need to know that, where the carbon is in your reactivity series. The three metals we have is magnesium, zinc, and what was the other one? Magnesium, zinc, and aluminium. Magnesium, zinc, and aluminium. So in terms of the reactivity series, we said that these are more reactive. So if they are more reactive, they will be faster. So be careful about rate of reaction versus how much product you get. The fact that you have a faster rate means you will produce the gas faster. You will produce more gas over the same time. Rate is higher when you produce more stuff in the same time. If I look at this, if I take a cross section, as you know in biology, you talk about cross sections. If I just take the cross section there at that time, which one produced the most gas in the given time? Which one produced the most gas? This one here, the green one there is A, and then the black one here is C. So that one is C. I meant to say that is C. And then I try another one. This green one here, this is going to be B. So what we can say here is the B is going to be slower, but then it becomes much faster there. It's slower there, but what you notice there then is it becomes so much faster. It's slow at first and then it becomes fast there. The slope will tell you the rate. So by right, we can see that A is faster than C, faster than B. So the rate is A is faster than C, faster than B. So the fastest one, the one that gives you the greatest number of volume of gas in the same time, that is going to be the most reactive metal. That should be magnesium. So A is supposed to be magnesium because it is the one that reacts the fastest. So fastest rate. But then that doesn't mean anything unless you can talk about the most reactive metal of the three. The most reactive metal from the three choices will produce more gas. Will produce more gas. That is actually wrong because I haven't completed the sentence. We know that that thing there doesn't produce more gas than B. So we're talking about produce more gas in a fixed time. So in a given time, before the reaction complete, in this fixed time, this produce the greater volume of gas is the fastest at the beginning there. So B is the slowest. B is aluminium. But we know that aluminium is actually more reactive than zinc. Why does the aluminium reacts much slower than zinc at the beginning? Well, you have to think about something called Al2O3, protective oxide layer. This one is stated in the syllabus. If you don't believe me, you can go through your metal syllabus. You know that aluminium can react easily with the oxygen in the A, and they will give you this protective coating. So after it reacts for some time, as soon as the hydrochloric acid, in this case, can come into contact with the aluminium inside, it will start to pick up the pace and become much more reactive. So, we already decided this was aluminium, not from the rate, but from the number of moles of gases there. So we know B must be aluminium. But in terms of magnesium versus zinc, magnesium is more reactive than zinc. So which one will be more reactive? So blah blah blah, zinc is the one that is less reactive, so slower reactions, but will still produce the same volume of gas because they follow the same equations, because Mg2 plus and zinc 2 plus have the same formula there. Obviously, this is talking about the third metal forming a larger volume. By right, I should be able to write this equation and explain it in there for that full 3 marks there. Okay, so what have I done here? I just want to show however amount of product you get, how much you get, is not necessarily how fast the reaction is. How fast is to do with rate. So how fast versus how much. Do not get confused between the two. So a faster reaction does not mean that you will get more products total, but it will give you more product in a fixed time, but it will not necessarily give you the most product overall, at the end of reaction. This is to do with rate. This is to do with amount, how much. So mole ratio and stuff there. Okay. I don't need to talk too much about catalyst. You should know the definition already. As I mentioned, speed up the rate of reaction, offers alternative reaction pathway with a new lower activation energy, itself chemically unchanged. What I'm saying is there are 2 marks there. Why do they give you 2 marks if you only write down it speeds up the rate of reaction? This is one of those things that students always ask. Why don't I get the full mark? Okay, well, you don't get the full mark because if you think about it, you're only providing 1 point. Why in the world would you get 2 marks if you only give 1 point? And why in the world do they give you 3 lines if they only want you to write 1 point? So you've got to think carefully. This is called exam skills, yeah? So we need to add in a couple of things, yeah? So we know that it will offer by offering alternative, or you say a different reaction pathway, a different reaction route, and this reaction route is a new lower activation energy. Okay, so overall the activation energy is becoming lower and therefore rate of reaction will be faster. You can probably add in like itself is chemically unchanged at the end of reactions. These are just, different kind of points of interest, but I would definitely give points for these two. This last one is more like a property kind of thing. You might get away with it. Chemically unchanged at the end of reaction. Now this next one is how we produce oxygen gas in the lab. This is a catalysis of this H2O2 going to H2O plus O2. So 2 of that and 2 of that, and that should balance the equation. So this is a liquid hydrogen peroxide, but actually it's an aqueous hydrogen peroxide dissolved in water, and you get liquid water and you get gaseous oxygen. Here you get gaseous oxygen. I think I asked Shakila earlier, but they can ask you the test for oxygen. Oxygen does not burn in oxygen, but you can put a glowing splint. Glowing splint is the one where the fire is no longer burning. So you just get like the flicker at the end there. So there's no more flame, but the glowing splint will relight in the presence of oxygen because oxygen support combustion. If you put oxygen to fire, the fire will grow even heavier and it's very dangerous, okay? So imagine when COVID was really serious, hospitals were running out of oxygen cylinder because we need oxygen to help those people to continue breathing, right? So hospitals have cylinders and cylinders of oxygen gas, and that's why when you see oxygen gas cylinder, there will be a big sign, do not smoke. If you smoke near oxygen cylinder, you are bringing disaster because oxygen, can if you have lighted splint, if you have like cigarette butts that still have flicker of fire and oxygen gas, not going to be a pretty story, especially for a hospital, yeah? So if you see someone smoking near oxygen cylinder, make sure you tell the police straight away, okay? So in this question, this is 4 marks. They're asking you for what happens to the rate of these reactions as time increases. This is about describe. And you need to talk about why the rate changes in this way. This graph is not a rate, but they ask you on the rate. So the first thing you must do is, rate is the change in the volume. Change in the volume of oxygen gas, because that is the product, so volume of oxygen gas produced. We're talking about gradient. We're talking about gradient. If you do math, you will know that gradient is the change in y over the change in x. This is 0 time. At 0 seconds, there is no reaction. If I draw a line here, this is called a tangent. This is a tangent. A tangent is a straight line, so a curve at time equal to 0. This will tell me initial rate. Initial means at the beginning. So this is the tangent. So the rate behave like that. So I can get a gradient of a straight line. It's very difficult to get a gradient of a curve, but we can draw a tangent and we can get the rate. As the reaction progresses, if I use a pink color, you will see that if I draw another tangent, the slope decreases, the gradient decreases, it becomes less sloppy. So if the gradient decreases, that means the volume of gas produced over time would decrease, that means the rate would decrease. And then finally, if you have this thing here in green, so there are 3 bits you can explain here. Here is horizontal line. You can walk on a straight horizontal path and there is no slope or anything because this is 0 slope. The change in y is 0. So that means your gradient is 0. And what is our gradient? The gradient of this graph is rate of reaction. So you have 0 rate here. Why is there 0 rate of reaction? Because reaction finished. Why is the reaction finished? Because your reactants must have been used up. So there is no more products being formed. There is no more reaction, no more products being formed. So what will you see at the end of reaction that tells you that is the end of reaction? What observation would you see in order to be able to say that there is no more reaction in this reaction setup here? I see Dania is around. Are you around, Dania? Dania Arisha? Dania Arisha? Okay. Hazira Damit has left the meeting. Okay, never mind. Hazwani Hidayah, are you there? Hazwani Hidayah, are you there? Hazwani Hidayah is not there. Let me see who else is around. Yeah. I can't really see everyone else. I don't know. Hazwani Hidayah is back. Okay, are you there, Hazwani? I don't know. Everyone connection is pretty bad, is it? Who else is around? Afika Farahia, are you there? Is Afika there?
Yes.
Hi, Afika. Okay, I hope the connection is okay. So this reaction will produce oxygen gas. You are collecting oxygen gas in the gas syringe. This is what you use to collect gas. Okay, so you don't allow the gas to escape because you have a seal here. So you collect the gas in the gas syringe. So as this reaction progresses, what would you see in this reaction? As this is happening, what do you see inside here? Any idea? So you have H2O2 in here, you have a catalyst, and then this reaction will produce oxygen gas. So what would you see in the solution if a gas is being produced? What do you think? Well, the rest of you should think as well, yeah? What do you think? Any thoughts? If you are producing a gas, have you ever done a practical before where you produce a gas? What do you see? We see bubbles because the bubbles indicate they are gases. And you cannot see colorless gas. You are collecting the gas and you can test the gas with a glowing splint and the glowing splint will relight. Okay? Anyway, my question originally was about what would you see at the end of reaction. When there is no more reaction happening, what would you see? What makes you say it's the end of reaction already? What do you think? What makes you say it's the end of reaction already? Are you still there, Afika?
I'm not sure.
Okay, so just now you will see bubbles. So at the end of reactions, would you still see bubbles being produced? Would there still be?
No.
Because no more gas is being produced, right? So no more bubbles. How about here? When there is a gas being produced, the gas syringe will move that way because the pressure, the gas keep on pushing it, the gas syringe will move that way. What happened at the end of reaction? Would the gas syringe continue moving?
No.
No, so the gas syringe will stop moving. When the gas syringe stop moving, is any gas being produced?
No.
That means the reaction has finished. Do you understand that this is the kind of question that will come out in alternative to practical? I don't know. I can't guarantee that all of you will be sitting for alternative to practical or the actual practical paper 3. We don't know. We really don't know what will happen. But as it is, you must be prepared for alternative to practical paper 4 as well, yeah? So everyone, just so we know that this is about rate. The question is not asking us on the volume of oxygen and time, they're asking on rate. That's why we must talk about rate, which is to do with the changes. I talk about the blue line. So I talk about the blue lines. The initial rate of reactions decreases. And I talk about the decreases as reaction progresses. Now I'm talking about the pink line. Why does the rate decreases as the reaction progresses? Why? Because as you use up the hydrogen peroxide, as more and more of these reacts, there are lesser and lesser of this reactant. If there are lesser reactant, they will collide less frequently. When they collide less frequently, then your rate will slowly decrease until everything is used up totally, then no more gas will get produced, then your rate will be 0 because no more gas is getting produced. Okay, so what we can say in general is the rate of reactions will decrease as reaction progresses because as the H2O2, which is the reactant or the reacting particles, get used up. When they get used up or they undergo reactions, there will be lower concentration. Lower concentration means there is lesser of the particles, therefore less frequent collision because there are less particles that collide, and then rate decreases until everything is used up. So I need to talk about until everything is used up, then the rate would go down to 0. So until that is not right. Until everything is used up, until all of the H2O2 completely reacted, and then when it completely reacted, then no more gas get produced, no more O2 gas is formed, reaction stop. It stops. So when reaction stops, rate equal to 0 because there is no more gas getting produced. 0 divided by any change in time, no change in your y-axis, no more gas getting produced, the gas syringe stops moving, the rate has stopped there. Okay, there are many more stuff, but you are now using the same mass of manganese 4 oxide, but you use a powdered form of the catalyst. So here we know the catalyst speed up the rate of reactions. So we are using the same catalyst. But now we use powdered catalyst. When we use powdered catalyst, will it change the volume of oxygen product? That's the first question. Will it change the volume of oxygen products when I use powdered catalyst? So let me ask, what do you think, Shakila? Will changing it to powdered catalyst change the amount of product I get? Will that happen? Shakila? Hello, are you there, Shakila?
Sorry, sir. Yeah.
I'm talking about using a powdered form of catalyst. Will it change the volume of oxygen produced?
Yeah.
No, because this is amount. So catalyst affects rate of reaction. You can use a lot of catalyst or you can use very little catalyst. It will not change the amount of stuff you get. It simply increases the rate of reaction. So that's the first thing you were wrong. So it doesn't change the amount. So here, if you use powder catalyst, it will still be the same. It will still be the same total of the volume of gas. If your reaction is faster, so I'm going to give you two alternatives now. If your reaction is faster, would it be this, number 1, or would it be this, number 2 here? Would it be the green color is not a good color. Would it be this blue color or the purple color? That is not a very good color as well. Let me change this to red. Will it be the red color light or would it be the purple color light when you use a powdered catalyst? Previously, you use a lumpy form of the catalyst. Now you use a powdered form of the catalyst. Will it be the purple line or would it be the red line? What do you think, Shakila? You are not sure. Okay. Let me ask Raihana. Are you there, Raihana? Hello, Raihana. Are you there? Hi, Raihana. So between this reaction and this reaction, so the blue color line, the purple color line, they produce the same volume of gas because I still have the same catalyst. Catalyst does not affect how much product I get. It only speed up. It only speed up the reaction. By looking at this graph, these are 3 different graphs. These are the original graph. And now I use a powdered form. Powdered form would mean greater surface area. So greater surface area because you crush it into fine powder. So greater surface area, rate should increase. There is an explanation. Rate should increase when surface area of the catalyst increases. How can you tell from this graph which one has a higher rate? Is it the red color one or the purple color one? Which one is faster? Which one has a higher rate of reaction? Purple or red? The purple is actually correct because rate is the gradient of this graph. the gradient of this graph is the change in the amount over change in time. Okay, Shakila, make sure you know that, yeah? So what I'm going to do is I'm going to draw a tangent. I'm going to draw a tangent to this purple color line. So this is the purple color line. And then I'm going to draw a tangent to this red color line. So you can see, so this is the red color line versus the purple color line. You can see the gradient, the steepness, it becomes steeper here because this reaction is faster. So this purple color line is actually faster reaction. And you want a faster reaction because the red increases. So it cannot be the red color one, it has to be the purple color one. Hopefully that makes sense there, Shakila. Okay, alright, so the rest of you, you should be able to sketch graph like this, yeah? So be very careful. I don't want to include the other one because sketch what will happen when you use a powdered catalyst. 2 marks there, 1 mark for still the same total volume of product because using a catalyst, changing the catalyst will not change how much you get, but it will change how fast you get the product. How much is berapa banyak amount, how fast is the rate, berapa kelajuannya. It produces the gas much faster. There is a lot more gas produced over the same time because rate is to do with change in amount over change in time. Okay, we don't have much time, but I thought that I'll open the floor for you to ask me any questions that you have from these past paper questions. You can tell me whether you want me to go through paper 1 or paper 2. It's really up to you. So, you know, the floor is yours. Not a lot of you remains. I don't know whether it's problem of connections or people are just coming in and out. I don't know. Okay, but anyway, so floor is yours if you wish to ask me anything. I can go through anything you want me to go through. Any questions from you guys? No questions? I don't know how strong is the connectivity, yeah? whether there's a heavy lagginess or not on your side, but I hope it is all right. I guess no question from you guys. Perhaps I need to go through a couple so that you will understand what's going on. So let me just go through this question then. Hopefully you will try and understand it better. Explain why the rate of these reactions increases as the temperature increases. This was what I mentioned earlier. You should be able to explain as temperature increases, what happens in terms of the particles. So we can say that the reacting particles, meaning the O3 molecules, will gain more kinetic energy. Kinetic energy is to do with movement. So when they gain more kinetic energy, it's due to the higher temperature, and then they will move faster. When they move faster, they will collide more frequently. And when they collide more frequently, what you can say is the rate would increase. So these are all the key points you need to answer this kind of question there. This diagram is not very clear, so I guess, well, maybe I should talk about it anyway. There are 3 marks associated with this question. This is about Haber process. Haber process, or Haber process, whatever you call it, is used to make ammonia. I talked about it earlier. You use iron catalyst. Iron catalyst, this is your transition metal as a solid. So describe and explain. So there are 2 bits to this, yeah? So what does catalyst do? Catalyst speeds up the rate of reaction. It makes the reaction go faster. That is the description bit. How does it make the reaction go faster? How does it make the reaction go faster? That's the second bit to the definition. So what the catalyst does is it provides a different or an alternative. You can use either word as long as it's your own word, I guess. A different pathway, a different mechanism, a different reaction route. What is important is it is with new, lower activation energy, and this will be faster reactions. This will be faster reactions because lower activation energy means that the rate will be higher. Now explain how the use of catalysts can reduce the overall energy requirement. So you know that this Haber process will take place at a high temperature because catalyst is not, catalyst is not easily, nitrogen is not easily reacted because you are reacting a nitrogen-nitrogen triple bond. So, you know, they don't react easily. So what we can say is, number 3, so nitrogen-nitrogen-nitrogen, well, nitrogen-nitrogen triple bond very strong covalent bonds to be broken. So that is why it has high activation energy. Very high activation energy. Now, it has very high activation energy, so it requires a large amount of energy in order to break it to kickstart the reaction. By using a catalyst, you can lower this activation energy, and therefore, how it can reduce it. This question is a bit tricky, isn't it? Describe and explain the effect of a catalyst. How the use of catalyst can reduce. I guess the lower activation energy, the new optional pathway, the new lower activation energy, is easier to overcome, and therefore this will reduce the energy cost in industry energy requirement there. Okay. As for this next bit here, so this bit part F, this is about a strong acid and a weak acid. This is magnesium and 1.0 mol per dn cube ethanoic acid. This is magnesium and 1.0 mol per dn cube hydrochloric acid. For 2 marks, you really need to be able to explain that, why one is faster than the other. So HCl is a strong acid. So define strong acid, it dissociates fully or dissociates completely or ionizes. If you want, you can use the word ionizes fully into H plus ions in water in solution. But then what we know is CH3CO2H is a weak acid. So what does a weak acid do? It only dissociates partially into H plus ions. If you dissociate partially only into H plus ions, so what we can say is lower concentration of H plus ions, even though they have the same concentration of the acid, but we are not talking about the acid on its own. We are talking about the concentration of the H plus. So focus on the concentration of the H plus. It's lower for the weak acids. So, less frequent collisions or collide less frequently. And if that is true, then your rate of reactions will be slower or lower for the weak acid and faster for the strong acid. Okay, so hopefully that makes sense there. In terms of these kind of questions, what is this? I think something is missing in this question. There's no way you can do this without knowing some values, so I'll probably skip that. And what do we have here? Blah, 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 blah. The diagram is not very clear. But if the diagram is clearer, you can see that, this reaction stops there. It is not very clear at all, so I don't think I want to spend too much time on it. But it is roughly around, no, that's not true. It is roughly around there, maybe, give or take. So 1, 2, 3, 4, 5. So that must be 90 cm cubed there. And when does it stop? It seems like it stops around there, give or take. If I just draw my line, I guess it's somewhere there, maybe. You might have a better luck if your diagram looks a lot better than mine. But this is 200, this is 250, this is 1, 2, 3, 4, 5. So this is exactly in between 225 seconds. The reaction has stopped there because no more gas gets produced. The reaction has finished. This is between carbonate and HCl. So you will get effervescence. You do not see carbon dioxide gas. You see bubbles. And when there are no more bubbles getting produced, that means the reaction must have finished. And you plot this kind of graph by collecting the volume of gas. And volume of gas can be collected using a gas syringe. 225 seconds and 90 cm cube. 225 seconds and you collect 90 cm cube. They are not asking us to do anything here. But we repeat the experiment. We have the same mass of calcium carbonate. So that means we get the same amount of gas. We get the same amount or volume of gas because we are not changing. We are not changing what has reacted. We use the same concentration of acid. And this is at the same temperature, 20 degrees Celsius, because this was done at 20 degrees Celsius. So there is no change in temperature. There is no change in your calcium carbonate. So it will still produce 90 cm cube. And you use small pieces. This is the exact same question as just now, using the catalyst. But here, this is your reactants. Your reactant, you use smaller pieces, still the same mass, so you should still get the same volume, but larger surface area would mean faster rate of reactions because you have greater contact area, and therefore your reacting particles can collide more frequently. So that is why your rate increases. It's 2 marks there because the first mark is you must be able to get to the same total volume, and because of the larger surface area, because you crush it into small pieces have a larger surface area, you expect it to be faster and not slower. You want the slope to be steeper. So what I can do is I can just draw. This is not good at all. Let me use this color. This is also not a good color. I don't know what would be a good color here actually. Let me use a blue color. I think that's probably the best I can do. Blue color. Like this. So that would be okay. So I finished the reaction earlier because the reaction is faster. I also have no reaction at time equal to 0. But if you see the initial rate, if I plot a line like this is the gradient at time equal to 0 for these blue lines, and this is the gradient at time equal to 0 for the black line. As you could see, this line, they become less steeper. So they become steeper, sorry. The gradient becomes steeper. The gradient is to do with the change in amount over change in time. That is to do with rate of reactions. So your rate is higher. Your rate is faster. And that is true because you are using a powdered form of the calcium carbonate, and that one will have a greater rate of reaction there. Last but not least, we are repeating the experiment, still using the acid. So it's not like we are changing the acid. And we use 2.0 mole per dm cube. This is the change here. Change the concentrations. Previously, you had 1 mole per dm cube. 1 mole per dm cube. This is hydrochloric acid, 1 mole per dm cube. And what else? Blah, blah, blah. And now you use 2 mole per dm cube. Use kinetic particle theory. Why the speed increase? Therefore, for 2 marks, you need to think about what happened to the particles as concentrations of the HCl increases. Concentration of HCl increases from 1 mole per dm cube to 2 mole per dm cube. What has happened is there are more H plus particles. We talk about greater number of H plus particle. There are more H plus particles per unit volume. If you follow the unit there, mole per dm cube. And if that is true, therefore, they collide more frequently. And if they collide more frequently with the other reacting particles, then your rate is going to be higher, increases there. Okay, I'm afraid that's all the time we have for today. So I've reviewed the whole topic. I've done a couple of questions showing to you how this kind of stuff work. And I'm sorry that we can't get everyone here. But before I leave, can we all just take a quick photo for attendance, please? So if we turn on our camera and just take a quick photo for attendance, and then we just call it a day here. So let's just quickly take our attendance. Otherwise, we might not have the evidence as they require. So what do I need? Actually, what do I need? Okay, so all right. So not too sure why that is not showing actually. Exit full screen. Let me see. Nope, I don't want that. Okay, never mind. So let's just do it here. All right, smile. 1, 2, and 3. 1, 2, and 3. Okay. Well, thank you everyone, and I hope that was helpful. So I'll see you next time. Okay. Thank you. Bye bye. The materials will be uploaded on the Google Classroom. Yeah. Okay. Bye bye.
Thank you, sir.
Okay.
Thank you, sir.